Hi, my name is Sadie Martin, and in this video I conducted a lab exploring Newton's second law and the momentum principle by videoing a tennis ball rolling across a flat surface and analyzing its velocity using the tracker software. I then used GlowScript to create a computational model and graph the ball's changing position and velocity over a set time. Newton's second law states that the net external force equals the change in momentum of a system divided by the time over which it changes. The change in momentum is the difference between the final and initial values of momentum. In this lab, I will compare the experimental motion of that tennis ball to the predicted motion of the computational model from GlowScript. The first thing I did for this lab was find the mass and the size of the tennis ball to use for tracker and the code for the model. The tennis ball had a mass of 0.0577 kilograms, and the radius of the tennis ball is 0.33 meters. In the tracker software, you can see that I have set the axis to be on the center of the tennis ball, and the ball follows the x-axis, and there is no change in the y-axis position. The tracker measures the distance the ball moves across the x-axis between intervals of time in seconds. Keep in mind that due to human error, the tracker cannot be 100% accurate. The points that I have marked vary slightly on the y-axis, and the ball may move slightly along the z-axis, although it is not tracked. Because of this, the data cannot be entirely accurate, but the changes are minuscule, so it does not make a big difference. By comparing the tracker data to the data of the model, we can see how much of a difference these errors make. The tracker creates a position versus time graph that is a linear slope indicating a nearly constant velocity. To create the computational model showing the ball's velocity over time, I modified the Lab 1 starter code to fit my scenario. The boxed outlines of code that you see on the right show the data that is specific to my video. On line 32, you will find the mass of the tennis ball. On line 35, you will find the ball's initial position taken from the chart on the left that I got from Tracker. Line 36 shows the initial velocity of the ball that I found by taking the second and third line of data from the Tracker table and plugged the numbers into Newton's second law, which is that the average velocity is equal to the change in position over the change in time. The data only consists of an x value since the ball is moving solely along the x-axis. Line 39 shows at what time the tracker started tracking the position of the ball, and line 49 shows the time the tracker stopped tracking the position of the ball. On line 54, the net force is set to 0 to represent the lack of forces applied on the ball in an ideal environment. Since the ball is only moving in the x direction, the force of gravity is not acting on the ball. The information inside of the while loop applies Newton's second law to update the ball's velocity as it moves along the x-axis. As seen on line 58, the new velocity is equal to the net force divided by the mass of the ball multiplied by delta t. The mass is a constant, but since the net force is equal to 0, 0 divided by any constant is still 0. This is multiplied by delta t. So as the time changes, it has no effect on the velocity of the ball. With all of this information, I was able to create a computational model of the scenario and two graphs showing position versus time and velocity versus time. Shown here is a side-by-side comparison of the position versus time graphs, the left taken from Tracker and the right taken from GlowScript. As you can see here, the experimental motion data follows the same path as the predicted motion data. There are few inconsistencies simply because for the GlowScript graph, we assumed that no forces were acting on the ball. But we can see from Tracker that there are small forces that in fact do act on the ball, such as air resistance and friction. In conclusion, because we used a round object and a flat surface, we were able to ignore the small forces that acted on the ball as it rolled across the table, giving it a near-perfect fit to the predicted motion. We saw in both cases that because the net force could be set to 0, as the ball moves across the flat surface, the velocity remains constant for the time observed.